For years, artificial intelligence was confined to answering questions and analyzing data. Now, the system begins taking action. We spent the first half of this decade entirely on the read path. This era was defined by the LLM. A large language model is an artificial intelligence program trained on massive amounts of text data to understand and generate human language. These were stateless, single-turn probability engines built to passively generate text. By 2026, the architecture has shifted to the right path. The new standard relies on stateful, autonomous digital operators. Instead of just reading data, these systems actively alter corporate databases and execute physical software workflows. This is Agentic AI. An agent takes a high-level goal, formulates a multi-step plan, invokes external software tools, and critically, observes the results to self-correct errors without human intervention. These are not experimental prototypes. Autonomous systems are currently operating in production environments, handling end-to-end enterprise operations from updating CRM records to diagnosing and remediating active IT incidents. Moving from passive generation to active execution destroys existing software models. It forces a complete redesign of how enterprise operations are structured. This line chart shows the market trajectory of Agentic AI, forecasting a massive compound annual growth rate toward a projected $52 billion valuation by 2030. To fund this expansion, enterprises are pulling capital away from legacy SaaS subscriptions, injecting it directly into agentic automation ecosystems. The business model for software is flipping. Buyers are transitioning away from paying for software seats that require a human employee to operate and are instead paying strictly for autonomous outcomes. Inside the modern enterprise, up to 40% of total AI budgets are now dedicated specifically to the deployment of these agentic systems. To survive this economic restructuring, IT leaders must understand the deep technical architecture making these autonomous outcomes possible. A persistent misconception in enterprise AI is that operational supremacy requires deploying a single, massive foundation model. The math proves otherwise. This graphic illustrates the emerging compute bottleneck. By 2026, inference workloads, the compute required to actually run the models, account for 2/3 of all AI compute, vastly outweighing the energy spent on initial training. Because of this density, enterprise priorities have shifted away from raw compute power. The controlling metrics are now execution latency, operational cost, and system reliability. The architectural solution is the DSLM. A domain-specific language model is an AI program trained on specialized, highly focused datasets to understand the exact nuances and logic of a particular industry. When tested against strict business logic, like financial compliance or ITIL standards, DSLMs consistently outperform generic models. ITIL is a set of detailed practices for IT service management that focuses on aligning IT services with the needs of the business. Because they are smaller and highly specialized, these domain models drastically lower both inference costs and carbon footprints. The foundation model is no longer a standalone monolithic product. It is merely a replaceable reasoning engine slotted inside a much larger execution environment. A language model cannot achieve autonomy on its own. It requires a durable runtime environment to hold context, manage state, and execute conditional logic over time. This schematic represents the graph-based architecture, which has become the 2026 enterprise standard for this runtime. Inside this graph, nodes represent specific execution steps, like pinging a model or executing a search tool. The edges connecting them represent the strict routing of information between those steps. The engine of this autonomous behavior is the React loop. React is a prompting framework that interleaves reasoning and acting steps to solve complex, multi-stage tasks. The process is systematic. The agent receives a goal, reasons about the immediate next step, executes an API call to a software tool, and observes the exact result of that action. An API, or Application Programming Interface, is a set of protocols that allows different software applications to communicate with each other. To persist data across continuous loops, the runtime maintains strict short-term and long-term memory, ensuring the agent remembers its previous actions and avoids repeating errors. The graph also applies dynamic tool selection, filtering the software tools available to the agent at runtime based entirely on its verified permissions and security clearances. This graph structure is what successfully transforms a static prompt generator into a persistent digital worker, fully capable of executing multi-step business logic. A single agent operating in a React loop is effective, but enterprise-grade execution requires multi-agent orchestration. This diagram shows the generation of a task graph. A complex prompt hits a central conductor agent, which instantly splinters the request, assigning distinct parallel subtasks to highly specialized subagents. This relies on a strict routines and handoffs methodology. When a task exceeds an agent's specific domain expertise, it autonomously transfers control and context to a specialized peer. In practice, this means a planner agent maps the project dependencies, an execution agent writes the required code, and an independent verification agent rigorously audits the output before deployment. To host these always-on digital proxies, hardware manufacturers and OS developers are now building dedicated physical computing infrastructure optimized entirely for continuous agentic operations. Through multi-agent orchestration, complex, month-long operational projects are executed, verified, and completed in minutes by a synchronized digital swarm. Granting autonomous systems write access to production databases and sensitive enterprise data introduces severe operational risk. Traditional LLM guardrails and system prompts are entirely insufficient here because those protections live inside the exact same process they are supposed to be guarding. This diagram displays the architecture of an isolated cloud sandbox. It physically separates the execution environment of the agent from the host infrastructure. An external policy engine sits outside the sandbox. It enforces strict constraints at the binary and network levels, making the ultimate control points completely unreachable by the agent itself. This architectural separation guarantees that agents can safely learn, invoke external tools, and evolve autonomously without the risk of privilege escalation. True autonomy cannot exist without verifiable containment. The security sandbox is the most critical, non-negotiable component of the entire agentic stack. Despite the technical maturity of these tools, 95% of enterprise AI projects fail to deliver measurable ROI due to poor underlying data infrastructure. ROI, or return on investment, is a financial metric used to evaluate the profitability and efficiency of an investment relative to its cost. The primary bottleneck is the 80-20 problem. Critical business logic is routinely trapped in unstructured, fragmented formats, like emails and legacy documents, that agents cannot reliably navigate or verify. Bolting an agent onto a legacy system produces friction. Agentic AI only delivers value when organizations use it to completely redesign their end-to-end workflows from the ground up. This comparative bar chart illustrates the potential of properly re-engineered systems. Teams integrating AI sales agents are seeing a brief 5.2-month payback period, followed by a 317% annual ROI. Redesigning workflows around agentic execution allows an enterprise to achieve predictable, scalable operational growth without a proportional expansion in human headcount. The technology is fully capable, but the enterprise itself must re-engineer its internal processes to extract these massive financial returns. As the workforce shifts from entirely human to a hybrid of human and machine identities, traditional IT management models are becoming obsolete. The CIO's mandate has shifted. They are now taking on the role of Chief Orchestration Officer. Their core mandate is no longer just maintaining software systems. It is managing, routing, and governing the secure flow of work between the human workforce and the autonomous digital workforce. This organizational chart highlights the most severe enterprise security threat of 2026, the shadow agent crisis. When well-meaning employees deploy unauthorized, autonomous AI plugins to automate their own tasks, they operate outside the official sandbox. This creates massive data exfiltration blind spots that easily bypass traditional security perimeters. Combating this requires KYA protocols, strict deterministic controls, and rigorous machine identity management. KYA, or Know Your Agent, is an emerging governance framework to verify, authorize, and track the actions of autonomous machine identities within a corporate network. The transition to the right path is complete. The ultimate competitive advantage now belongs entirely to the enterprises that can securely orchestrate, govern, and scale this autonomous digital labor force.